Welcome back. It's time to look at the metrics and some quantitative principles of cache memories. You have already seen this metric before, but let's formalize it. By far, the most common metric expressing the performance of a cache is the miss rate, or its reciprocal value, the hit rate. The miss rate is defined as the number of misses divided by the number of references done. Hit rate is essentially the same thing, but focusing on the hits rather than the misses. Since we want a very high hit rate, this number is normally over 90%, and then it might make it easier to see small differences expressing it as a miss rate rather than the hit rate. Here's a simple example. Assume that a program makes 67,354 data accesses during its execution. 56,756 of them hit in the cache. The hit rate is then 56,756 over 67,354, which is about 84.2%. Conversely, the miss rate is 1 minus 0.84 or 100 minus 84.2, which is 15.7%. Having the hit rate or miss rate, we can use this to calculate another important metric, the average memory access time, which is defined as the hit rate times the hit time plus the miss rate times the miss penalty. The miss penalty includes everything from fetching the block from lower levels in the hierarchy to restarting the pipeline. We often express then hit time and the miss penalty as the number of clock cycles, but quite often real times like nanoseconds can be used also. Here is an example calculating the average memory access time for a system with an 84.2% hit rate. Hit time is 1 clock cycle and the miss penalty is 10 clock cycles. And so the average, with this formula, the average memory access time will then become 2.422 clock cycles. How does cache performance come in play with the CPU performance equation? If every memory access is a cache hit and the hit time is 1 clock cycle, then no modification is needed. But to take cache misses into account, we need to calculate a new effective CPI, where the number of stalled cycles per instruction caused by cache misses needs to be added. The number of stalled cycles due to memory accesses can be calculated as the total number of accesses times the average memory access time expressed in clock cycles. Let's look at an example. The table shows the frequency of a number of instruction classes and the CPI of each class. Otherwise, let's assume that the instruction cache hit is 100% and that the hit time is 1 cycle and that the miss penalty is 10 clock cycles. The task is to calculate the effective CPI. Calculation is done as follows. We take the weighted average of the CPI for each instruction class where the relative frequency is the weight. This yields a base CPI of 1.32. Then we need to calculate the number of memory access per instructions. This is essentially the relative frequency of load and store instructions, which means 0.28 plus 0.0006, which is 0.34. The average memory access time can then be calculated as shown, and we get 1.225 clock cycles. When calculating the effective CPI, we take the base CPI 1.32 plus 0.34, the number of accesses per instruction, times the miss time, which is 0.225. Note that we have subtracted the hit time 1 from the average memory access time. The effective CPI becomes 1.4 about. So we can conclude that branches and jumps contribute to 0.32 extra clock cycles per instruction, and data cache misses contribute an additional 0.0765 extra clock cycles per instruction. Now it's time to dissect what a cache miss really is. We can classify the misses as such. A compulsory miss is the first miss which is caused by the first access to any memory block. We cannot get rid of these. A conflict miss is a miss which occurs because of the limitations in address mapping in the cache. A fully associative cache does not have any conflict misses. As a rule of thumb, you could estimate that an 8-way set associative cache has almost zero conflict misses and behaves as a fully associative cache. Any other miss that happen is said to be a capacity miss, as they are mostly affected by the size of the cache. When we introduce multi-core processors later in the course, we will also see a fourth kind of miss called coherence or communication miss caused by threads executing on different processor cores and which communicate through shared memory. The most important design parameters we have talked about so far are the size of the cache, the degree of associativity in the address mapping, and the size of the cache line. Replacement algorithm and write strategy are not unimportant, but they are second-order effects. Here are some basic ideas on how the basic design parameters affect performance. Large caches reduce the capacity misses. With the same line size, they will also reduce the amount of conflict misses, simply because there will be more lines in the cache. However, the hit time will increase, and you typically can't build a larger cache than 8 to 32 kilobyte and still be able to do a cache access within a clock cycle. Higher associativity reduces the conflict misses, but a drawback is that it increases the hit time. Larger line sizes are almost as good to begin with if the cache is large enough. When you bring more data to the cache, you reduce the compulsory misses. It, however, may increase the amount of conflict misses, and it definitely increases the miss penalty. Let's see the result of an experiment about this. This graph shows the miss rate for 4 caches of different sizes as a function of the block size or line size. The caches are of size 4 kilobyte, 16 kilobyte, 64 kilobyte and 256 kilobyte, and the line size changes from 16 bytes to from 32, 64, 128 to 256 bytes. The first observation is that large caches lower the miss rate significantly. The second observation is that with increasing line sizes, the miss rate improves to a certain point. However, beyond this, for smaller caches like 4 kilobyte and 16 kilobytes, the performance goes down again when the line size increases further. For larger caches, the miss rate does not go up, but it does not go down either. Furthermore, there are other negative effects with too large cache line sizes. The miss penalty, which affects the overall performance, goes up with large cache lines. You often read an entire cache line and then select the correct word, and this means that the power consumption also goes up with larger cache lines. This graph shows the miss rate for different cache sizes subdivided in different types of misses. The compulsory misses are so few, so they are basically not visible here. For most caches, the dominant type of misses are capacity misses, which can be mitigated by increasing the cache size. However, note that the direct mapped 16 kilobyte cache one-way has roughly the same miss rate as an 8 kilobyte two-way set associative cache. As a rule of thumb, a direct mapped cache with size n has the same miss rate as a two-way set associative cache with size n over 2.